Very good. So I would like to thank the organizers for the opportunity to speak at this conference. So I will speak about this subject, non-abelian Hodge correspondence and cohomological whole algebras. So I made the title a bit more precise compared to the title of the abstract, which was a bit more general. And so I mentioned too many results to be able to speak about everything. So in this talk, I will concentrate on non-abelian Hodge correspondence applications of the theory of cohomological whole algebras. And I should mention that this is partly joint work with Ben Davison and Sebastian Schlegel-Mejia, both based in Edinburgh, and also partly work in progress. So feel free to interrupt me at any point if you have some question or if I'm not precise enough. So the main topic is non-abelian Hodge theory, and this is some relationship between three kinds of objects one can consider on a smooth projective variety, X. So the first objects you may want to consider are local systems, that is representations of the fundamental group of the variety, with some fixed points, some fixed base points chosen. You can also consider Higgs bundles on X. So this is something a bit more geometric. So a pair of a vector bundle together with some Higgs field, and the Higgs field is some OX linear map between F, the vector bundle F, and some twist of F by the sheaf of one form. And you impose some integrability condition like this. So theta squared is 0. Also, we want some vanishing condition for chain classes. And since in this talk we will concentrate on curves, so when X is a curve, a smooth projective curve, this amounts to fixing the degree of the vector bundle to 0. And the last thing one can consider are flat connections. So flat connections, we see that from the definition, it looks very similar to Higgs bundles. And also in spirit, it's almost the same thing as local systems, because one can get a local system from the monodromy of a flat connection. And so the definition is a pair F theta with theta like this, but this time it's not OX linear, as in the case of Higgs bundles, but it satisfies the Leibniz rule. And again, we have some integrability condition. So as I said, in this talk, we have X, a smooth projective curve, and this is already a very quite difficult situation. And it's the framework of the P equal W conjecture, which was proven recently, last year, but stayed open for 10 years. So the categories we will consider as the following. So I repeat a bit what I said. So we have a category of representations of the fundamental group of some curve C. We have the category of semi-stable Higgs bundles of degree 0. And so where semi-stability means the following thing: for any subsheaf G of F stable under the Higgs field theta, then you want the degree of F to be negative, non-positive. And for connections, you take the category of vector bundles with flat connections on the curve. One of the main results of non-abelian Hodge theory is that all these three categories are equivalent, and the equivalents are through some category of harmonic bundles, which is something of more analytic flavor, and it's not going to appear in this talk. So when one has these three categories, we would like to parameterize objects in these categories. And this is the subject of modular theory. So one can proceed classically as follows. So first we frame the objects, that is, we fix a point on the curve, and we identify the fiber, the stalk of the object at this point. For example, the stalk of the Higgs bundle at this point with some fixed vector space. And adding this framing will give some moduli space of frame objects, and this moduli space is something very nice in the sense that it's some algebraic variety. And to remove the framing, we have some action of general linear group changing the framing. So what one really wants is the quotient of the moduli space of framed object by this general linear group. And this is something geometric invariant theory can deal with very efficiently. So in our three situations, we obtain three moduli spaces of framed objects, so which I denote by R, with some sharp. Sharp is something, so either Dolbeau for the Dolbeau moduli space of Higgs bundles, or Betty for the moduli space of local systems, or theorem for connections. And C is the curve, and R is the rank of the local system or connection or Higgs bundle. And this is the output of the construction of this moduli space of framed object. It has some GLR action changing the framing, and taking the GIT quotient gives some new space, M curly M, which parameterizing semi-simple objects in the corresponding categories. And one could do something a bit fancier, that is considering static quotients. So I will say a word on this later. It's so because this language is a bit unnecessary, but it's just like taking the quotient of this space by the GLR action without taking the quotient in some sense. So keeping all the information of the action. And as I said, a framed object is some objects with the fiber at some point which is fixed, identified with some vector space. So it's a way of rigidifying the moduli space. So now we can put the picture of non-abelian Hodge theory in this big diagram. So on the outer circle, we have the moduli spaces of framed object R, Betty, theorem, and Dolbeau. And inside, we have their GIT quotient, so quotient in some algebra geometric sense. Non-abelian Hodge theory gives bijections between the moduli spaces of framed objects, so the outer maps in this circle. All these maps are bijective, but not continuous. So only one of them is continuous, and it's the Riemann-Hilbert map, which associate to some connection on X. So X is C everywhere. So, but this picture is true for any X, any smooth projective algebraic variety X. You associate the local system, which is given by monodromy of the connection. And the other two maps, so, are only bijective, but there is a counterexample for continuity. But once you take the quotient, so you go down to the inner triangle, all these maps are still one-to-one, and they become homeomorphism. So even a bit more than homeomorphism. So this map is still complex analytic. This map is real analytic, and so is this map. So taking the quotient gives maps with better smoothness condition. A question of Simpson, who constructed moduli spaces in this way and proved many results in non-abelian Hodge theory, is, so can we compare the GLR equivalent geometry of the representation spaces? And the purpose of my talk today is to explain how one can answer positively this question. So first, I would like to illustrate this non-abelian Hodge correspondence for a smooth projective curve of genus 1 when the rank of object is 1. So small r is 1 here, which is not written on my slide. And in this case, the Betty, so a local system of rank 1 on the curve is the choice of 2G scalars, which is a space homomorphic to the circle, 2G powers of the circle, and I think some 2G is missing, so 2G powers of the positive real numbers. And the Dolbeault moduli space, which is the choice of a line bundle together with a Higgs field. So you can identify it with the cotangent bundle to the Jacobian of the curve. And these two algebraic varieties are homeomorphic, but the like you can't find an algebraic homeomorphism, algebraic isomorphism between them, because the Betti moduli space is affine algebraic variety, while the Dolbeault moduli space has a non-constant map from a smooth projective variety, which is the Jacobian of the curve. So it can't be affine. Right. So as I said, I will say a word on stacks. So only global quotient stacks appear, so quotient of some algebraic variety by some group. And what it means in practice is that we are studying equivariant geometry of some spaces. And we can just leave the language of stacks and adopt the language of equivariant geometry. If, for example, some stack is quotient of some X algebraic variety by G, then when we compute the cohomology or Borel-Moe homology, what we are really doing is computing the equivariant cohomology and equivariant Borel-Moe homology. And this is done by the Borel construction. So we fix some contractible G space, and we build this space X times sub G E. So this is the product X times G quotiented by the diagonal action of the group G. And there is a typo here, so you don't need this quotient by G because the quotient is already included in this thing. If G is C star, the group of non-zero complex numbers, then you can take for E infinite affine space minus the origin. And it has an action of 6 star by rescaling coordinates. And this action is free, and this space is contractible. Okay, so now, we would like to apply cohomological Hall algebras to studying non-abelian theory. And cohomological Hall algebras are powerful tool to study Borel-Moe homology of moduli stacks of some categories. And if the moduli stack is M sharp, where sharp is, as in our previous examples, Betti, Dolbeault, or the RAM, we can construct an algebra structure on the Borel-Moe homology of this vector space. So this thing is a vector space, a huge vector space, because M sharp is something quite big. And we can enrich this vector space with more algebraic structure. It makes it easier to study because we have more stuff to say about this. And how do we proceed to construct this product is by considering this diagram. So we take two copies of the stack of object, and on the left-hand side, and one copy on the right-hand side, and in the middle, the stack of short exact sequences. So short exact sequence is just 3 objects, so M, N, and something E in the middle. And you can project by Q sharp like this by keeping the right and left objects, and by P sharp just keeping the middle object of the short exact sequence. And for the categories we consider, we have some very good homological properties, which translates into some geometric properties of the maps Q and P. So P is proper map, and Q is quasi-smooth map. So it means, in terms of Borel-Moe homology, that we can pull back by Q in Borel-Moe homology, and we can push forward by P. And if you want to build a product, this is exactly what you want to do. You want to be able to go through this diagram in Borel-Moe homology, so pulling back by Q and pushing forward by P. And so doing this procedure gives the product on the Borel-Moe homology like this. So we started from a category, we took the stack of objects, then the Borel-Moe homology, and we end up with some algebra structure. So I will say a bit more about this pullback, virtual pullback, for this map from the stack of short exact sequences to the product of two copies of the stack of objects. So I wrote here what it means for this map to, so what property this map has for it to be quasi-smooth. So it can be presented as the classical calculation of the total space of its tangent complex. So in explicit terms, we can find a three-term complex of vector bundles on the product m sharp times m sharp, like this, v minus 1, v0, v1. And this three-term complex induces some vector bundle stack on this product, so which I wrote v0 by v1. So this is some this has to be understood as some vector bundle, something a bit more fancy, but vector bundle on this product. And if you pull back v1 on this quotient, then you get a vector bundle on this quotient, and d0, the differential d0, gives a section of this, so a map like this. And you can identify the stack of short exact sequences with the zero section of this map. And so now virtual pullback is done in two steps. So you first, to pull back to the stack of short exact sequences, you first pull back to this fancy object, vector bundle stack. And then, so you're here, and you can pull back to the zero section, to the zero locus of this map. And both operations are easy to define, and it gives the virtual pullback for the map Q. Okay, so I just wanted to say that once we have some good presentation of the morphism Q, performing the pullback is something quite explicit. So now I will say a bit more on cohas, cohomological whole algebras, and BPS algebra. So this Borel-Moore homology can be presented as the cohomology of some constructible complex, which I denoted this way. So I don't want to spend too much time on definition of this object. But this object is constructible complex on the moduli space, and it has the property of being concentrated in non-negative cohomological degrees. So we can just take the degree 0 cohomology, and this happens to, by this proposition, to be an algebra. So I define everything as mixed-range modules, but this is like some upgrade of category of constructible complexity. And so this is an algebra object for some monoidal structure, and this monoidal structure is defined in this way. So if you consider the direct sum map from the moduli space to itself, so the product of two copies of moduli space to the moduli space, then you can define some dot product, box dot product like this, by first taking the exterior product of the two objects and then pushing forward by this direction. And this is the monoidal category in which the BPS algebra lives. So the main theorem, our main theorem on BPS algebra is the following. So if you take C, a smooth projective curve of genus at least 2, then you have the following. So this BPS algebra happens to be a free algebra. So it's generated by intersection cohomology of the moduli space, and there's no relation between generators. And the full cohomological whole algebra, so this constructible complex has to be understood as full cohomological whole algebra, is isomorphic as complex of mixed-range modules to the symmetric algebra in this fancy monoidal category of something, and this something is some Lie algebra to which we extended by some polynomial algebra. So this thing is star equivalent cohomology of the point, which is some polynomial algebra. And this Lie algebra is nothing but the free Lie algebra generated by the same thing. So we started from quite a fancy geometric context, and we end up with like quite easy to describe algebraic object. And from this, we can see that things don't really depend on this sharp symbol. They only depend here, where in the intersection complex. But by non-abelian Hodge theory, all the spaces M sharp are homeomorphic to each other. So if we consider everything in category of constructible complex, this constructible complex doesn't depend on this sharp symbol. And so in the three geometric contexts, Dolbeault, Betti, and the RAM, we get the same thing. So the full Coha here, there is a mistake that don't coincide as complexes of mixed notch modules, but they coincide once you forget the additional weight structure and you consider them as complexes, constructible complexes. So what we would like to do is to compare these objects, which are algebra objects, as algebras and not only as complexes of constructible complexes. So first you have to compare. So we have three contexts: Betti, the RAM, and Dolbeault. So first we will compare Betti and the RAM, and this thing is rather straightforward by the derived Riemann-Hilbert correspondence. So this derived, it gives some identification of the cohomological whole algebra diagrams, so the induction diagrams we use to define the product. And so in particular, the cotangent complexes to the map Q for Betti and the RAM are isomorphic, and so the virtual pullback coincide. So we obtain quite straightforwardly that these two cohomological whole algebras are isomorphic. Now, if you want to compare the RAM and Dolbeault cohomological whole algebra, you need to use what is called the Hodge-Deligne boundary space, which was an idea of Deligne to interpolate between Higgs bundles and vector bundles with flat connection. So you consider the space of lambda connection, where this time nabla is some map like this, where there is some twist by lambda. So if lambda is 0, this factor disappears, and you get a Higgs bundle. While if lambda is 1, then you exactly get a connection on the vector bundle E. So as before, you can construct the moduli space of framed objects, frame lambda connection. Consider either the static quotient or the GIT quotient, and just recalling the parameter lambda gives you some maps like this to the affine line. And so the fiber over 0 corresponds to the Dolbeault situation, while the fiber over 1 corresponds to the Durham situation. So the main theorem in progress is that this constructible complex, so if you push, so P is the map which goes down all the way to the affine line, so from the stack to the affine line. This thing has locally constant cohomology sheaves, which means that the cohomology of the fiber doesn't depend on the point of the affine line. And since A1 is constructible, you can rewrite this constructible complex as the pullback of the push forward at some point, where pi this time is the map from A1 to the point. So this thing, it's constant over A1. And from this property, you get as corollary that these two cohomological whole algebra, so this one, the RAM, which is the fiber over 1, and this one, Dolbeault, which is the fiber over 0, are canonically isomorphic. So we can upgrade the identification of their cohomology as an isomorphism of algebra objects. So the proof, in the next 2 slides, I give some ideas for the proof. So we have these 2 maps like this. So this map I denoted GAH, like Jordan Holder, and this map is now P. We can construct by Koha procedures some Koha products, cohomological algebra product on this object. And as I said already, if you fix a point in N1 and you take the fiber over this point, you can recover either the Dolbeault. I mean, for lambda general, you get lambda connection. And you have some geometric properties of this constructible complex. So it's concentrated in non-negative relative perverse degrees and in absolute perverse degrees bigger than -2. And also, as a complex of mixed modules, this thing has non-negative weights. So I mean, I think the only thing I need to say is that we make fundamental use of the relative perverse T structure of the constructible category for this morphism P, which was introduced by Hansen and Scholze a couple of years ago. And then from the 3 properties I wrote on the previous slide, we get that the restriction of the intersection complex of the whole Hodge moduli space to some fiber is exactly the intersection complex of the fiber. And we have some canonical morphism from this intersection complex to the cohomological algebra of the Hodge moduli space, from which we can construct by product this map. And this map is an isomorphism, because to prove it is an isomorphism, we can do it fiber by fiber. And if you restrict to the fiber over lambda in A1, you either get Higgs bundles or connections. And in both situations, we know that the corresponding map is an isomorphism. So this map is also an isomorphism. And this proves this result. And last, I will give some further possible developments. So what one could work with objects with parabolic structure, so parabolic Higgs bundles. One could also consider spaces in positive characteristics and try to compare their cohomology and Borel homology. And the first point is about other applications of the relative cohomological Whole algebra relative perverse T structures introduced by Hansen and Scholze in this context. So 2 applications are Schiffmann's positivity conjecture for Katz polynomials of curve, and also deformation invariance of some invariants, so BPS invariance, BPS cohomology for quivers. So I'm running out of time, so this was my talk.